Yeah, so welcome to today's discussion on heterocyclic compounds. Today, what we do is today we'll be picking up another new class of heterocyclic compound we know as azole. Okay. Now, can anybody tell what actually this name signifies? Azole. What are the information you can extract by just this looking at this name? Can anybody tell? So what does it indicate? What are the informations just this short name will tell? So it has two parts, right? One is aza, another is ol. So what information you will get?
Nitrogen, sir.
Yes, nitrogen. One is the presence of nitrogen, definitely. Another information, OLE. Who can tell? What does OLE mean? OLE is, first is it is 5-membered, unsaturated, right? So that means this compound, this class of compounds must have one nitrogen and a 5-membered fully unsaturated ring. Now it can have any more elements, okay, hetero elements beyond nitrogen. So nitrogen should be there. Along with nitrogen, some other heteroatoms may be present, okay. And that's why these classes of compound has been divided into two parts. One is 1,2-azole, where you have two heteroatoms. They are directly connected through one bond. So you have, that's why you have 1,2 atom, 1,2-azole. Another is 1,3, so two heteroatoms. They are connected with two bonds. Okay, so that's why they are 3-atom positions, so 1 and 3. Now in this type of compounds, you have 1,2-azole with three different compounds, where one is the pyrazole, another is isothiazole, and the third one is isoxazole. So isoxazole, so one O has been vanished, so isoxazole. And the 1,3-azole, you have imidazole, you have thiazole, and oxazole. Okay, so these two are 1, 2, and 1, 3. Definitely, they are just the isomer of same structures. I mean, the same formula. Okay. Now we'll first go through the 1,3-azole, and then we'll quickly look into 1,2-azole. So 1,3-azole, as we have come across that, it is it includes imidazole, thiazole, and oxazole. So this is imidazole, where the one position you have NH. This is 5-membered ring, and you have one N is at sp2, another N apparently sp3. Okay, but actually, if you look at that nitrogen also, we can take it as sp2 in terms of the resonance. Okay, so the lone pair can take part into the resonance. Now you have thiazole. So here one position is the thiol, I mean the sulfur, and if you look at the oxazole, definitely the one position will be the oxazole. So 3-number atom, that is common, and that is the aza. Okay, and number 1 atom, that is varying. Now this type of compounds, uh, since they are nitrogen containing compounds, our thought is always what will be the basicity, because nitrogen containing compounds we generally uh, use as the base. Okay. Now you come across in the last class uh, the basic property of indole and pyrrole. Okay, they are much lower than the pyridine, and you have come across the value of pKAH. So indole you have seen around minus 2.4, pyrrole you have seen around minus 4, and pyridine you have seen 5.2. So pyridine was among that three was the most basic, right? Now here, when you come to imidazole, the scenario will be completely changing. Now, if I give the value, imidazole is having pKAH, so pKAH 7.1 is quite basic, okay, much more basic than uh, pyridine, okay. And this one, thiazole, is still basic, though it is not as basic as pyridine, but it is much more than what you have seen for indole. So you have the pKh is 2.5, and when you move from thiazole to oxazole, your pKh is 0.8. So can anybody quickly tell why such thing is happening? If you move from imidazole to oxazole, okay, your pKh is falling, decreasing. So can anybody tell how actually it behaves if you add H plus? So which nitrogen is going to take that proton? Who can tell? If you use H plus, which nitrogen in the imidazole will take that proton?
Between 4 and 2 nitrogen.
Between 4 and 2. So you can tell nitrogen number 3, okay? Yeah, so that is correct answer. So actually what happens, though you have sp3 apparently looking, okay, many people may do the mistake, because generally we know sp3 lone pair of electrons are easily accessible than sp2, okay. But as I told, this is apparently sp3, but actually it behaves as sp2, okay. So what happens is that it goes this way, so it takes that proton. Ultimately you will have that this is your structure, you will get it as, okay. And this structure is, now you can understand, it is symmetric structure. So you have like this way, you can have, okay, the charge can move from one end to another end, getting. So that's why if you look at these two, you will not be able to distinguish, right? These two structure, they are exactly identical, okay. And due to that fact, your pKa is a bit higher. Now when you move from nitrogen to sulfur, definitely your electronegativity is dropping, okay. But you have a situation of third orbital, means you have 3p and 2p overlap is happening here. So if you consider the s, Okay. Though your electronegativity of S is lower than nitrogen, but you have 3p 2p overlap is happening. Okay, that's why uh, the affection towards the proton is decreasing. Okay, and in case of oxygen, it is the electronegativity which is more, I mean, predominating. So due to that electronegativity of oxygen, uh, the electron will be preferring to stay with oxygen, rather it will be donated. Okay, so this situation is highly diminishing, and that's why you have a very poor basic property. Okay, so hope you got these points, how it varies, and why it is varying that much. Now we'll come to the synthesis. So synthesis of 1,3-azole, you have a couple of synthetic route. So the route 1, one 3-azole can be assembled from component providing the 2 heteroatoms. For example, you have thymine and thymidine and amidine, okay, and alpha haloketone. So either you just take these two or these two, you will get the compound. Okay, so structurally, if I give, you have a alpha haloketo, this is alpha haloketo, okay, and you have one unsaturated compound. Okay, you have Z here as the heteroatom, and you see, look at the structure here. You have the 5-membered ring with Z here and nitrogen here. So this nitrogen is being intact, and here you have the Z. So halo is being replaced. Okay. Now, if I tell you, I want to get this as my compound. So what will be my starting material in this route? Can anybody tell? What are the starting material you will have? Can anybody quickly tell? So write the starting material quickly just by this route. Looking at this route, what will be your starting materials? Can anybody find out? What will be the starting materials? Quickly.
You done, sir?
So what you do is you try to find out the starting material. If I give this as your, sorry, I have one N here. If I give this as your substrate, what will be the starting material based on this synthetic route? What are the starting materials? So you will have one alpha haloketo and another unsaturated compound.
Ketone.
No, don't just do like this. You write the structure in your pen on the paper, and then you tell this is the compound 1 and that is compound 2. What is the compound 1? If I tell this is compound 1 and this is compound 2, what will be the compound 1 for this case, this structure? What will be the 1 and what will be the 2? look at this one. So your one will be, you have pH double bond O, then you have halo system. So you have ethyl here, you have here halo. So halo you can take bromo. So this will be your compound 1. I'm taking bromo, you can take chloro or iodo also, but bromo is more suitable. You can easily prepare that one because you have bromine and brominating reagents are very easily accessible. What will be compound 2? Compound 2,
Amide.
compound 2 will be, you have methyl here, so you have methyl, then you have double bond O, then you have NH2, right? So these two will be the starting materials for this particular compound. Now your job is how the mechanism will be happening. Okay, so you should try the mechanism. How the reaction will proceed. So you have this one, look at, you have this keto, you have amide, and you have halo. Okay, so one is you can think about the elimination of water, okay, this H2 and this oxygen. Another is this halogen is being eliminated by the reaction at the center. Okay, now you come up with the proper reaction mechanism for this particular reaction. Okay, so you should try the reaction mechanism. Now this is what kind of route, if I tell what is the retro, if you think about what will be the route of this particular reaction. So you have, if you look at this G, I mean the Z1, 2 and nitrogen 3, okay, and here the 2 carbon. So this is 3 plus 2 route, okay, this is 3 plus 2 route. Got it? So this way you can find out. Now you have another route. So the second route 2. Route 2 is this one. So the other way is to do the reaction between the anion of isonitrile and aldehyde or thioaldehyde or imine. Okay, so isonitrile, anion of isonitrile. Okay, so this is the isonitrile. Okay, NC connection. Cn is the nitrile. We call the isonitrile is the opposite. So this anion, and you have one unsaturated system. Okay, this two is producing this one. Now here, if I give kind of imidazole, if I want to make, the imidazole, what will be the situation? Let me write the structure. Suppose I want to make this imidazole. Okay, so what will be my starting material? Can you tell what will be the starting material? So if this is compound 1, this is compound 2, what are the starting materials 1 and 2? So quickly try what will be the starting material as 1 and as 2. So 1 and 2. What will be those? So if you look at this part, okay, so N C this the whole thing, okay, is coming from here, and this part is coming from this. Okay, so now you tell me what will be the one, what will be the isonitrile species? So your isonitrile, you have to have one anionic species. This is already, this is isonitrile, you have to take one anion. Now here I have given one methyl, so you should have one methyl here, and then you have one anion. Okay, and this part, what will be the compound 2? The compound 2 you will have, for this case, this part you have to consider. Okay, so that means you have ethyl, okay, double bond NH, and you have one, this is, you look at, you have hydrogen here, okay, but there I have given one phenyl. So this isonitrile, you have to change it to this negative charge. You have one phenyl, or phenyl can be attached later on also. Okay, and this is, you have a hydrogen. Got it. So these two you have to react to find out the structure. Now, before going to this complicated one, what I will suggest for you is to come up with the actual reaction mechanism, how the isonitrile will react with this unsaturation to form this azole. Okay, so that reaction mechanism also you should try. And if you are not able to do that one, then let me know. But don't just tell me, sir, I am not able to do. You should try and then you tell me. Okay, so these reaction mechanisms I am escaping. This is your job. You should practice. So everything I'll not give you. Okay, so you should try by yourself some of the reaction mechanisms. Anyway, so let us move to the reactions itself. So reactivity of 1,3-azole, here I'll give the summarization of the overall reactivity. Okay, so this is how we find the reactivity. Now it looks very haphazard, but still if I explain, maybe you'll be able to get it. So this is your 1,3-azole, okay, 1,3-azole. Now this 1,3-azole, if we use the electrophile, what we find is that 1,3-azole prefers the electrophilic reactions at the 5 center. So generally this is 1, 2, 3, 4, 5. Okay, the 5 center is found to be most electron dense center. Okay, and that's why the C-centered reaction, electrophilic substitution, will be preferred to the position 5. Okay, now I'm not giving the reactions themselves. Whatever electrophilic reactions we have discussed, you should consider those are the reactions, kind nitration, halogenations, okay, the acylation, those type of reactions what you have seen, that will be happening at the center 5. Okay, carbon number 5. Now one thing is that if you use the base, okay, to abstract the proton, and then you do the electrophilic reaction, okay, particularly if you have this Z as NH or imidazole, okay, then what we see is that it is the two center, 1, 2, 3, 4, 5. It is the two center which gets activated during lithiation. Okay. Now, generally, if you use the base is going to take proton from the NH, because that is directly connected with the nitrogen, most electronegative atom here in this ring. So the proton will be abstracted, and if you use the electrophile, definitely that N will be reacting with the electrophile. Okay, so that's why it is given. This is kind of N protection. Okay, now if you use the lithiation, what we see is that it is the two center which will prefer the lithiation. Okay, lithiation will be preferring at two center. So that means two centered reaction. If you want to do substitution at two center, what you have to do? You have to do first lithiation, and then you have to react with the electrophile. Understood? But if you want to directly do the reaction at the 5 position without lithiation, I mean, do the electrophilic reaction without lithiation, the reaction will be taking place at 5. Okay, so this is very interesting. You can do selective electrophilic reaction at the 5, and you can do selective electrophilic reaction at the 2. For two-centered reaction, your reaction should go via lithiation. Okay, so that is the point you should note down. Now, among these 1,3-azole, the oxazole, we find it does reaction, cycloaddition reaction it does. And here, if you look at, you have this is okay, so your reaction is happening. You have oxygen here. This is your I mean the furan system, I mean oxazole system, and oxazole system is reacting with this one. Okay, this alkene, and you have this 5-membered ring formation. Okay, now it is quite easy. If I write here, you'll understand. You have, suppose this is oxygen, okay, 1,3 position. So and this one. So what is going to happen is Diels-Alder type of reaction. Okay, and you have the formation of this one. Okay, you have N here, and that is happening. Okay, so now the stereochemistry and all, you are going through the Diels-Alder chemistry, so you should know which one will be up, which one will be Okay. So diol-Salter reaction we also find for uh, oxothiazole. Okay, and the stereochemistry, I think you are well known. It's well known to you. Now, one more thing is that what will happen if you just add proton? So definitely you have come across, it is the nitrogen which is going to take the proton. Okay, and you will have this form. Now this form, you see the delocalization, and this proton, if you can abstract, you will have a deuterionic form, and this deuterionic form can further generate the carbene. Okay, so you have this one NH, and this will be carbene. So that means you can easily generate carbene from 1,3-azole. Okay, to generate carbene, what you have to do, first you have to protect the N, okay, or you can do protonation, and then you use base selectively to extract the proton from this carbon to generate the anion, and that anion, I mean this deuterionic compound is equivalent to 1 carbene. Okay, so the carbene chemistry can be obtained from this particular azole, means 1,3-azole. Okay, so these are the important parts. So if I summarize what you will see, the nitration or halogenation kind of reactions can go to the 5 center. If you do lithiation, will take place at 2 center. If you, it can undergo diol-Salter reaction, okay, and you can generate the carbene. Okay, so these are the important part of 1,3-azole. Now quickly, one reaction, displacement reaction. Suppose you have one halo at this center and you are using a nucleophile. Since you have nitrogen here, so it will act as sink. So what will happen? It will take that electron, okay, and then that electron will come back to generate the pi bond, and halogen being a good leaving group, so it will come out. So you'll have just the displacement of the halogen with the suitable nucleophile. Okay, so this is one important reaction. Remember, this reaction will not happen if you use suppose butyl lithiated hydrocarbon. Okay, in that case what will happen, lithiated hydrocarbon do lithiation at this center. So instead of attacking the carbon, it will attack to the halogen, and you'll have the negative charge here, and then lithiation will happen. So this is the general reaction we have seen for lithiation. Now another is kind of activation. So what we can do is, if you have the carbon at this methyl or ethyl, whatever it is, if you have R at the C2 center, this R, if you have the carbon with hydrogen, what you see, that hydrogen becomes acidic if you do the N protection. So that means if you treat with say if I give this one, okay, and treat with methyl iodide, what will happen? The methylation will take place here, and you have a positive charge. Okay, and now if you have here CH3, if you use the base, that hydrogen become acidic. It can easily take, because this is stabilized. Okay, and you can do now electrophilic reaction at the center. Okay, so electrophilic reaction. Okay, so that is, you can do here electrophilic reaction. So these are the two other reactions of 1,3-azole. Okay, as usual, if you just have bare azole, you just treat with butyl lithium, lithiation will happen. And here you see how the carbene is generated. Okay, so as I told, this is become acidic. So if you use just the base, it will take the proton and it will be negative, and this negative is equivalent to this carbene. So you can have carbene chemistry. Now quickly 1,2-azole. So 1,2-azole, this is the structure here where X is the different heteroatoms and nitrogen is fixed there at 2 position. Okay, so examples, you have pyrazole, you have isothiazole and isoxazole. Okay, now pKh, the 1,2-azoles will have lower pKh than 1,3-azole, means they will be less basic with comparatively the 1,3-azoles, the similar compounds. Okay, so that means imidazole will be more basic than pyrazole, thiazole will be more basic than isothiazole, and oxazole will be more basic than isoxazole. Synthesis, to produce 1,2 and 1,3, 1,2-azole, you have the reactions here. This is 1,3-dicarbonyl compound. So 1,2,3 dicarbonyl compound, and you have 1,2. So one nitrogen source, and there is other heteroatom source. So you can do the reaction. So for example, if you want to do 1,2-isoxazole, then this will be what you will have to use the hydroxylamine NH2OH. Understood? So this will be utilized for isoxazole synthesis. So you have this nitrogen. This is, if you want to synthesize, you have to use this one. And another part, you have to use the 1,3-dicarbonyl. So here, this if you break down, so you will have this will be your starting material, hydroxylamine NH2. Okay, so you just take your own examples and break down and try to find out different starting materials, and again redraw the reaction mechanism. So all the different reaction mechanisms I have shown you previously, how different groups are reacting and all. So you just need to practice and you should be able to do. Second is kind of example here. You see, this is the hydrogen derivative. So if you try to generate the pyrazole, and if you try to generate the oxazole, you'll have thiazole also, thiohydroxylamine. So you have to use. Now another reaction is you have the reaction between if you look at 1,3-dipolar cycloaddition reaction of nitrile oxide. Okay, so nitrile oxide and this you are reacting to generate this one. Now examples, this is an oxide and this is the double bond source, so you have 1,3 reaction. Okay, so this is the root. You just need to heat it and your product will form. For the pyrazole, you have to use the corresponding N derivative. Okay, and you will get it. How will make the N oxide? Generate the nitrile, you take it and treat with hydrogen peroxide and base, so you'll be able to get the N oxide. Okay, so this way we make the N oxide. Now reactivity quickly. Here if you look at the bare electrophile will react at center 4. Okay. The lithiation happens at center 5. Okay. It is just it is different than 1, 3. So these are the two important points you should note down. And the other case you have if electrophile after generation of anion or pyrazole, and this is X will be connected to the nitrogen, that is general one. And N will be methylated, that is also general one, it's not so difficult. Yeah, so these are the main thing. So the main point here is the electrophile direct will be reacting at center 4, but via lithiation it will be reacting at center 5. So these are the two important points. Nucleophilic displacement of 1,2-azole, you have halogen. If you here, definitely you have double bond, so it is the same thing. Nitrogen will act as sink and it will fall here and halogen will come out, so you'll have a displacement reaction. But if you use with butyl lithium, the lithiation will take place here, and then you have other nucleophilic substitution, electrophilic reaction. Okay, so these are the general intermediates, general route I have shown. Now you should come up with the reagents and all and do the reactions. Okay, so nitrations, always prefer to do the nitration non-protonatic reagent. You can easily generate the nitration. Halogenations, generally we use the bromine as the source for bromination, along with some heating or lowering temperature. Chlorination, you should use the chlorine gas along with some ferric chloride or like that activator. Okay, so those things, and iodination is quite easy. You just need to use iodine and do some heating. That type of thing will be doing halogenations. So these are the different things. You just go through and practice the reaction mechanism. In the next class, we'll be discussing the diazine. So I'll try to finish the diazine in the next class. So some selective reactions and in a coincided manner we'll be discussing. You just focus on this one. This will be helping in your exams. Okay, and the remaining classes I'll be taking on the photochemistry. So hopefully in the next week we'll have those classes. Okay. So if you don't have any questions, we'll close here. Otherwise, can 1 minute if you have any doubt, 1-2 minutes. Anything is there to ask? Okay, then.
Sir.
Yes, tell.
Sir, reactivity of 1,3 azoles reaction is last middle
day.
reaction.
Let me check.
So
1,3-azole, right? Which reaction? Let me. This is this slide. This one you are talking about? Which one? You got disconnected or?
so formation of cycloadact. This one, yes, sir.
Yes.
Formation of cycloadact on reaction of oxazoles with dimethyls.
Okay, so what I'm telling is that this 1,3-azole, they can act as diene in Diels-Alder reactions. Okay, and in that case, since we have two double bonds here, that two double bonds will act as diene. Okay, so you have two centers here. If you take the oxazole, you have this is the center and this is the center. Okay, so if I clearly write here, you have sorry, this is the oxygen. Okay, 1,3 center. So if I so this is the oxazole, right? Now this one, if you react with diene, any diene, so what is going to happen? You have the diol-Solder reaction. Okay, so diol-Solder reaction will take place, and you will get the corresponding this product. Okay, now here the R1, this R, which site it will be? It will be based on what are the groups. Okay, generally to avoid the stereo, I mean, since these two are, it looks outside. Okay, to avoid the to avoid the crowdedness, what will happen? This dienophile will come in such a way that the oxygen and this R will be in the opposite direction, so that your crowdedness will be decreasing. Okay,
Yes, sir.
and generally the oxygen, this is towards the inside, right? So the diene, what happens, the inside bonds will go up, and that's why your oxygen is upwards direction. Okay,
Okay, sir.
yeah, and the R, okay, it can come also this way, right? This is the same thing I'm telling. It can come also this way, the same thing, the same compound. Okay, and the compound will prefer either coming this way or coming this way, these two directions. Okay, now when it will come this direction we call it the R is outside. This direction we call the R is inside. Okay, now if the R is inside for dienophile, what will happen? That will go down. The inside bonds will go down and outside bond will go up for dienophile. Okay, now it will prefer to come, it will prefer to come this way because it will have less crowdedness in its transition state. Okay, because oxygen is already upward direction. If the R is coming towards upward direction, then you'll have more crowdedness, right? That's why it will come to a way to decrease the crowdedness in the excited state, I mean the transition state. So the R will be inside one. So this will be the actual approach. Okay, and that's why you see the R is down. So here the R are down. Okay, hydrogen is small, so it will be upward direction. So you'll have less steady. If the R is there, you'll have more steady because R is different group. Got it? So this is the thing. Okay, so you
Yes, sir.
just try your I mean the concept clear and try to do more study. Okay, try to do practice the reaction mechanism and all. Okay, so we'll meet in the next class. Thanks for your attendance, attending my class. Thank you.